Okay, perfect. Well, thank you very much, Don. Okay, let's see here. Well, there we go. Okay, welcome everyone. Pleasure to be here. Pleasure to have all of you here today on this very snowy day here in Ottawa, at least. But great to be here. So today, what I'm going to talk about is about mud and mudstone, and in particular, two sedimentological motifs: mud that is either planar laminated and structureless. So let's get started. So mud and mudstone. Here we have a succession of mudstone, that of the Billings Shale. This is a local outcrop here in Ottawa, just south of Innes Road. And it's a fine-grained unit. And historically, I mean, mud and mudstone fine-grained sediments have been described as dull, boring, and homogeneous. And this is a classical interpretation and description of these sediments. And what I want to show today, or at least show to all of you, is that these rocks they're the most interesting group of rock, whether sedimentary, but they're the most interesting rocks to work with. Okay, and they are highly heterogeneous, not homogeneous for the most part. So what is mud? Mud is simply a mixture of silt and clay-sized sediment between 62.5 microns to 4 microns. Okay, and so by definition, it's if you have a mixture of sediment, if more than 50% of that sediment consists of silt and clay-sized sediment, then it's mud. And so mud that undergoes lithification becomes mudstone. Mud rocks, shales, silt stones, clay stones, the terminology is vast. And so here we have an example. So this photograph is that of a bedding plane, a hand sample showing the bedding plane, of a hand sample. And so here we have silt, which is the light colored layers, and clay, which is the finer layers. And so, I mean, this is the fine-grained sediment, finer than sand size. So two kind of broad research questions that I want to answer today, or at least address, is what is the microtexture and microfabric of mud and mudstone? And so these terms, whenever you see the term micro added to that of a word, it just means, these are characteristics which are resolved using microscopy. These are petrographic terms. So how does, that's the first question. What is the microtexture, microfabric of mud and mudstone? And how exactly does microtexture influence reservoir properties? So just quickly, I mean, microtexture, this encompasses features such as grain size, shape, sorting. Microfabric would encompass the orientation and arrangement of clay particles, framework grains, any diagenetic constituents, pores and pore types, things of that nature falls under that of microfabric. Okay, so how do we examine fine-grained sediments? Well, you can examine them at the outcrop scale, but what that will lead to is likely a rather homogeneous description. And I mean, most of the the kind of classical descriptions of fine-grained successions have been based on observations that are revealed at the outcrop scale. So to truly understand what is the texture, the fabric, the composition, what sort of sedimentary structures are present, you have to make thin sections. And so how do we do that? Well, we sampled a number of successions. We impregnate the mud blocks, either mud or mudstone blocks, with resin. We slice thin sections. This is actually this is a high resolution thin section scan of unconsolidated mud, that of the last glaciation, deposited here in the Champlain Sea basin. I mean, look at the textural heterogeneity from top to bottom of the thin section. And so thin section petrography is done using just a classical optical microscope. And that gives you, that would provide details at the millimeter scale. So to truly characterize features at the sub-millimeter scale, well, then we examine the thin sections under a scanning electron microscope. And so the resolution that's revealed, kind of combined between optical and electron microscopy, you can determine details from a millimetric scale to a submillimetric scale. So I want to show 3 case studies today, and just kind of generally, Pascal formation is Cretaceous in age. It is what we call a clay mineral rich succession, meaning that more than 40% of the clay-sized particles consists of clay minerals. And so this is I know this is an Ontario conference, but this locality is in Alberta. And so what's shown this on the screen here? On the left is, this is a high resolution thin section scan. I mean, look at the textural heterogeneity. That sedimentary structure that you're looking at is planar lamination, okay, which consists of a rhythmic alternation between silt-rich layers and clay-rich layers. See, this is partly shown as that of a scour fill. This is actually a shell fragment, if I can zoom in on my cursor, but that's an Inoceramus bivalve shell fragment, an extinct genera of clamshells. So mud is either planar laminated, or it's structureless. Here's another example. Planar laminated mud. Again, look at the textural heterogeneity. The light colored layers are silt rich, the dark colored layers are clay and organic matter rich. The upper part of the thin section scan is bioturbated. That's why the nice horizontal layering is kind of it's mixed up near the top. Bioturbated just means it's been chewed up by organisms. What B shows here, this is an SEM image of the magnified white square in the thin section scan. And we can further magnify that on the area shown in C. This shows the textural detail of a silt-rich layer and a clay-rich layer. Again, look at the heterogeneity. I mean, also take note of the scale. That's a 10 micrometer scale bar, meaning that these lamina are on the order of a few tens of microns thick, 0.01 millimeters in thickness. I mean, that is remarkable that this type of organization exists at this scale. So SL and CL refers to silt-rich layers and clay-rich layers in all of the subsequent images. What do we see at, what is that of the matrix? So this is a highly magnified view of the mud. And so mud in a clay mineral-rich sediment consists of what we call domains. And so domains comprise 2 to 3 clay particles that stack in parallel alignment. And these are typically on the order of about a micron in diameter. And domains are further packaged into what we call face-face aggregates. These are often 1 to a few micrometers in diameter. And so it's domains and face-face aggregates which make up the mud fabric. Let's look at another example. This of the Ordovician Billings Shale. This is an Ontario case study here in Ottawa, for example. Also clay mineral rich. We see the same sedimentological motifs that we see in the Pasquascal Formation. Mud is either structureless or it's planar laminated. If we look at the SEM scale on the next slide, again, look at the textural heterogeneity. Note the scale bar, 50 micron scale bar. The same structure that we see in the Pasquascal Formation, we see in the Billings Shale. Clay-rich layers that are sharply intercalated with silt-rich layers. The silt-rich layers in this case, and I should also note that silt-rich layers are well sorted. Okay, the sorting is excellent. The clay-rich layers are poorly sorted. Here's the mud fabric at a highly magnified view. Again, the same type of hierarchy that we see in the Pasquascal Formation, which is clay mineral rich, we see in the Billings Shale. Domains which are further packaged into face-face aggregates. Now let's look at an example of a clay mineral pore fine-grained succession, meaning that clay-sized particles are dominated by non-clay minerals. What are they dominated by? In the case of the Lake Candona Champlain Sea mud, they're dominated by quartz, by feldspars, by hornblende. So here we have an example, a photomicrograph on the left, again showing planar laminated mud, silt-rich layers, clay-rich layers, structureless mud on the right. The lowermost part of the succession, that of the Lake Candona succession, it's glacial lacustrine. Here's glacial lacustrine mud, the same intercalation where you have silt-rich layers that are sharply overlain by clay-rich layers. We also see this in the glacial marine part of the succession, meaning that basin fluid chemistry serves no control on whether the basin fluid was freshwater or saltwater, serves no control on the presence or occurrence of planar lamination. What about the microfabric? So for example, here we have the Lake Candona Champlain sea mud, it's clay mineral poor. And when you compare that with a clay mineral rich sediment, it is a completely different fabric. Okay, so clay mineral rich sediments, which make up majority of fine-grained successions, well, they contain an abundance of clay minerals. Why? Because clay minerals are where they source from, they're sourced from weathering. What makes the Lake Candona Champlain sea mud succession so interesting is that the amount of clay minerals is it's not negligible, but it's low. So how exactly does that affect the occurrence of planar lamination? None at all, meaning that clay mineral pore successions show the same textural heterogeneity and the same sedimentary structure as that in clay mineral rich successions. And so now this is important. Why is that important? Because historically, previous interpretations for the origin of planar lamination rely upon clay flocculation as a requisite process. And so Bill Arnott and I, we would argue that clay mineral flocculation serves no requisite control on the origin of this sedimentary structure. And we published a paper very recently last year in a journal on the origin of planar lamination. If you're interested in reading about that, we have a discussion on previous interpretations, and we proposed a mechanistic model. If you search planar lamination in Google, it's either the first or second result, and it's open access. You can have a read if you're interested. Okay, so how exactly does a mud or mudstone microtexture influence hydrogeological properties? So the majority of those of you in the audience today are consultants or hydrogeologists. So how exactly does the properties of fine-grained sediment influence things like porosity, permeability? Well, here we have an SEM image, that of the Pasquascal Formation. And so what you can see is that there's kind of two kind of broadly defined intervals in this image. The upper part is full of cement. You have dolomite cement, there's some quartz cement, calcite cement. This is well sorted, coarse silt to very fine grains, sand-sized sediment. And it's loaded with cement, meaning that, why is it full of cement? Well, because the sediment was well sorted, and so the highly porous and permeable substrate, well, this likely facilitated ion transfer by interparticle flow that led to significant cements developing, probably during very early diagenesis, based on the size of the cement crystals are quite large in this image. Whereas the clay mineral rich sediment that you see in the lower part of this image, well, interparticle flow was hindered. And so, lower permeability, there is a lower abundance of cements that are present, although there is pyrite. There's a significant amount of pyrite, of which the pyrite is spatially associated with organic matter through bacterial decay of organic matter under sulfate-reducing conditions. Okay, here's another example, the Billings Shale. And so what you see in this example, here you have, just like in the Pasquascal Formation, well-sorted, silt-rich sediment, almost completely cemented, overlain by poorly sorted clay-rich sediment. So again, ion transfer by interparticle flow, because the sediment itself is porous, it's permeable, you have considerable cements infilling pore space. What about that of the Champlain Sea mud, the Leda clay? And so, this mud forms, it's in the Ottawa and St. Lawrence River valleys. It's an regionally extensive aquitard, which has been studied quite extensively. And so, for those of you who are familiar with this fine-grained glaciogenic part of the succession, you'll know that it's fine-grained. I mean, it is really fine-grained. It's really clay-rich. But there are some intervals in the succession which are silt-rich, like what you can see in the upper part of this slide. Here we have this nicely well-stratified sediment. There's no scale bar, but the silt in the upper part of the image is medium to coarse silt. All of the black that you see is resin. This is a well-sorted, porous, permeable sediment, and in contrast, the clay-rich sediment, which is shown in the lower part of the slide, it's poorly sorted, likely is porous. We know it's porous because we've the porosity of sediment is about 60 to 70% porosity, but low permeability. And so it is the texture which results in, which may lead to local zones of enhanced water flow, like in the example of this silt-rich, well-sorted, porous and permeable sediment. Okay, what I want to sort of conclude with is what is the potential reservoir significance? You're kind of leading to the geomechanics. I know this is a hydrogeology groundwater conference, but just to end on the note, so this map shows the distribution of North American shale plays. I mean, these are unconventional reservoirs in North America. Some of the, most famous, get a lot of media attention. You have the Permian Basin, Eagle Ford, the Bakken Shale, the Marcellus, Utica Shale, number of different fine grain successions. But I'll tell you, the commonality between all these successions is not just their fine grain size, but it is the ubiquitous nature of planar lamination. Planar lamination is a ubiquitous feature in the fine grain sedimentary record. These are core photograph examples from many of those successions, and your eyes can pick out that, yeah, it's planar laminated. This fine grain sediment is planar laminated, and we don't see this, this is not exclusive just to the ancient. We see this in the modern as well. Mississippi fan on the left, Mediterranean Sea on the right. What do you see? You see planar lamination. You also have some structural intervals, mud, which is structureless. So what does this mean? Well, that's important because having an understanding of the textural attributes may serve to better understand things like stratal rheology, fracture development, and even hydrocarbon migration. So the silt-rich layers that we see, the silt-rich layers are composed of brittle quartz and feldspar minerals, and the brittleness of these layers increase with the presence of any rigid, hard diagenetic cements, things like quartz, apatite, dolomite. We saw this in the previous slides. These silt-rich layers in planar laminated sediment, they are well cemented. So rocks consisting mostly of brittle minerals, these may be susceptible to fracture under applied stress, whereas rocks that are rich in ductile clay minerals and organic matter may deform plastically and undergo significant strain prior to fracturing. So why is that important? Well, the brittle silt-rich layers may act as planes of weakness that may be prone to cracking during hydraulic fracturing, and the regional distribution of these lamina, both on a vertical and horizontal scale, a lateral scale, may imply that once hydraulically fractured, they may provide laterally continuous extensive fracture networks and ultimately migration channels for the extraction of hydrocarbons. And so this interplay between brittle and ductile forces in planar laminated strata, again, the most ubiquitous, I would say, feature of fine-grained sediment, then raises a fundamental question, an important question for future research, one being, does hydraulic stimulation result in sub-millimeter scale lamina-bounded horizontal fractures? And so I just want to conclude, this is a succession in eastern British Columbia, Cretaceous succession, mostly mudstone-dominated strata. This is Quaternary sediment from the last glaciation, major unconformity near the top. And so again, the two major motifs, sedimentological motifs, you have planar laminated mud, you have structureless mud. There's even a third if you consider biotubated mud. Those are the, call them the three most common sedimentological motifs, and they directly control the textural property. I mean, the textural properties directly control both the hydrogeological properties, but also the reservoir properties of these sediments. So a little bit over time, but I'll end it there. And thank you to the presenters for the invitation and for all of you for the time today. Thank you.